Here we are. Good morning. It's the physics video lecture. Physics 4B, video lecture 10. So I had a lot of questions about the last couple of homework assignments. So much so that we may do the entire hour just problem review, and we'll see how far we get. We can always finish a little earlier, start the new chapter. Let's just have a look. Let's check this out here. Yes, so I have a list here, and I'll put them up. This is all from chapter 21. So let's just call this homework review chapter 21, and the problems are 35, 51, and 52. These two actually go together. That'll be good. 64, 69, 74, and 81. Okay, quite a bit going on here. The first one, and what's good about these problems is we're reviewing our point mechanics skills, really, because we're doing vectors, a lot of vectors, and good to review these skills. So let's have a look at 35. So 35, we have, here I'll go over here and get a bigger picture. So for problem 35, we have this symmetric situation where here's an x-axis, here's an origin with a lowercase q charge, and then along on a semicircle, we have these uppercase q's. So over here, that's a distance r from the origin, and then we have them here and here, apparently at 45 degrees. So it doesn't matter if the force, if these are like or unlike charges. By the way, all of these here are capital Q, and this one here is lowercase q. So let's just assume they're same sign of charge. And then we're just going to ask what's the force acting on this one at the origin due to all of these charges. Now symmetry plays a role here because we have a repulsive force, so this top charge here, the force in that direction, and this bottom charge, the force in that direction, directed equal and opposite. They cancel each other, they do nothing. The charge here is doing a force in that direction, and strictly speaking, I can make all of these arrows exactly the same length. And because I can do that, I think I will lengthen them a bit. Right? The magnitudes of these forces are all the same, being K, Q, Q over R squared. Those are the magnitudes. Okay, let's make these a little bit longer just so that we can get a better drawing. Okay, so those are these forces. These two have canceled completely. Now, we've only missed these, and they're at 45-degree angles with the same magnitude. So, and this one here is pointing in that direction. So we're adding all of these vectors up. I could do a little indication that we're all on this semicircle here. So here goes. The net force by symmetry, it's in the x direction because these two here have a cancellation along the y-axis. We could define a y-axis like that. So they have a cancellation here. The resultant is all in x direction. And we should be able to just write it down. Fx, we have k q over r squared times 1 for this thing here, plus 2 times the, get a third color here, 2 times the projection, right? Both of these here have a projection in the x direction. and that's 2 times the cosine of theta. Okay, so that's 2 times 1 over root 2. And then it's in the I hat direction, and you're done. So 2 over root 2 is the same as square root of 2. Square root of 2. So 1 plus the square root of 2. Okay, that's a nice problem. This is chapter 21. So we have that one. Okay, there were other problems with the same type of technique. I'll next look at problem 74. Okay, so let's look at problem 74. I had set that one up. I thought that was a good review of some of the skills you had from last semester. So right now we're looking at these 2 pendula that have charge on them, and a consequence of that is that they repel each other, and they're of length L, mass M, same over here and here, and there's an angle theta. Okay. So let's use a different color for our free body diagram. We have here mg. We have a tension. This angle theta is found there as well. And we have charge, so we should put the Q and Q on here. So we have charge so that there's an electrical repulsion, and the whole situation is symmetric, so if we just analyze this one, we'll be good. Okay, so let's see what we have here. We have, we'll do the y-axis first, so let's declare our coordinate system. So the y-axis is pretty clear, minus mg plus t cos theta equals 0, right? We're doing F net force is equal to 0. The x-axis, we have, pointing to the left, t sine theta. Okay, that's that projection over here. Okay, t sine theta. And pointing to the right, we have the electrical force, which is k q squared over, now this separation distance squared, that separation distance is 2 sine theta, and we have to square that, so that equals 0. And this one must have had a minus sign because it's pointing to the left, so not a plus sign. So what we're going to do next is just eliminate the tension, because the tension is equal to mg divided by cos theta. So we can go ahead and plug that in and bring this to the other side. We're going to have k q squared 2 sine theta. Oh, missed something here, didn't I? I missed a length. Okay, got to catch these things in real time. L sine theta, so 2L sine theta, quantity squared. So kq squared over 2L sine theta, the quantity squared, equals t sine theta, bringing that over to the right side, and t is equal to mg over cosine theta, so we're looking at mg sine theta over cosine theta. Okay. Yeah. Divided by cosine of theta, which is a tangent theta, and I'll leave it here, making sure I didn't miss anything. Okay, cosine theta. Yeah, so if you go ahead and solve for q squared, and they take the square root, okay, cross multiply, divide by k. So I'll just write here, etc. We're done. So that's problem 74, and really something off of last semester, except with the addition of this electrical force. In the lab, you can actually do this kind of thing and charge up some usually very light balls of the, say, the weight of a cork or something, so small, lightweight objects, and you can get that repulsion to happen. Good, so 74. So what's next here? And it's a logical sequence that I'm looking for these problems. Yeah, problem 64. Problem 64 is kind of interesting. Also an interesting mechanics problem, actually. So problem 64, we have a charge Q, a charge 2Q, some object, and a third charge 4Q. Do I have that right? Well, they were lowercase in the picture. Fine, we'll go with lowercase. It's actually a pretty clever problem. So Q, 2Q, 4Q, and they are tied together with a string, and the separation distance is D. Okay, so we have a string here, separation distance D on both of these. And because these are all repulsive forces, there is a tension. There are tensions in the string, T1 and T2. So this is just an interesting one to set up. Okay. If you go ahead and start with this charge here, okay. So here's Q. What are the forces on it? Obviously, the tension is pulling to the right, okay. And we don't know what it is. It's T1. Now, for there to be a tension, there must just be repulsive forces due to these two charges, and of course that's the case. Okay. So I'm just going to write here F electrical, and the equation we set up now is going to be T1 minus, and it'll be these two forces. So the force between these here, remember separation distance D, will be KQ times 2Q divided by D squared. And then the repulsive force due to this charge over here will be KQ times 4Q divided by 2D, the quantity squared. Okay. And this is static, so that equals 0. We can see that we're going to have T1 is equal to, so what do we have? 4 over 4 and 2. So we can just bring this to the other side, and we already have 4 over 4 is 1, and 2, we have 3KQ squared over D squared. So that's one of those tensions already. Let's send this one up. Now it's possible to next do the force on 2Q here in the middle, and you'd have tensions in both directions. But it turns out it's sufficient to just deal with the one on the right side. So for 4Q, we're going to have 4Q, that's the charge. And what do we have? We have T sub 2 pulling to the left, and an electrical force pulling to the right due to the repulsion with those other two charges. So T sub 2 is pulling to the left, we have minus T sub 2. And then for the electrical force to the right, we have K 4Q times 2Q divided by D squared. That's these two, 4Q, 2Q, D squared, plus K 4Q 4Q times Q divided by 2D quantity squared equals 0. Okay, vectors equals 0, so T2, bring that over the other side, see what happens. So T sub 2 is equal, you see again we're going to have K Q squared over D squared. We just got to pull out the factors here. Here we have 4 times 2 is 8. And here we have 4 divided by 2 squared plus 4 is 1. So we end up with 9K Q squared over D squared. Interesting problem. And if you were to set up the middle one and do it, the equation for it, you'd see it consistent with these two, and you'd be done. So that takes care of problem 64. These are all pretty great. Now, what else do we have here? '69. Yeah, this is okay. Now 69 is a good problem here. I'll put it up there. So next we're going to do 69. This is a good problem, but it's not good to have to plug numbers in. We're just going to make a picture and discuss the physics. Okay, so we're doing a balance. This is actually not uncommon. So we've got a massless balance, and we have a length L to here, and we have two charges separated by D, distance D, and we have a Q1 and a Q2 there on top and bottom. So Q1, Q2. Okay. So first of all, we start with attraction. So there's an attraction here, and we have to hang some mass on this side to balance it out. Okay, we've got an attractive force here, wants to pull this balance down and to balance it out. So let's go ahead and call this length S. Got to name it something. And of course, gravity is pointing down in that direction, so it's a balance. So yeah, what do we have here? We have the force times the lever arm, and the force is, so we're looking at a torque, tau is equal to, and then we can either balance the torques or we can make the counterclockwise one be positive and the clockwise one be negative, okay? So that torque will be, counterclockwise will be positive, it'll be K Q1 Q2 divided by D squared times L. That's the torque counterclockwise, and the clockwise torque is just going to be minus mg times s. Okay. And for it to balance, the net torque is equal to 0. So asking for numbers, they do that in the book, but we just wanted to see this here. And I think we were supposed to solve for n, okay? The second part of the problem was also interesting because they asked us to move this mass over to this side. Do it in a different color. So if that's S, they said, well, put it over here at a distance S. Same mass. Okay, so this is part 1. And the next part, same mass. And what would the charge have to be? Well, apparently you'd have to have the same sign of charge because you'd need repulsion. But actually, the interesting thing is, it would be the same equation with a minus sign here and a plus sign here. So the answer to that, what the Q2 was supposed to be, or whichever one they ask you to change, is that it would be the same magnitude as before, but with the opposite sign. So if you bring the mass here over to this side, change, so same magnitude, opposite sign, which is to say you turn them into the same sign. Okay. I'll just write change sign of charge. Change the sign of one of those charges, okay? Here you had attraction, here you have repulsion. So attract, and here you have repulsion. Okay, so that's a nice little mechanics problem as well. In fact, it reminds me of a lab we used to have where instead of electric charges, we would be measuring magnetic charges in wires that would have been in and out of the board here, but it was also done using a balance. Okay, so nice problem. Good. Okay, so the last two problems, same as my comment before. We're going to treat these two as a single problem, okay, and then we'll do this one. We're not interested in the numbers so much as setting it up. Numbers will be important too, but only after we set it up. So let's set that one up. This had to do with electric charges, charged particles, electrons, protons, in a certain constant electric field. And that was what I had ended with the other day. So this is 51 and 52. And here's the thing, we have force is equal to Q times electric field, and we're given an electric field and it's in newtons per coulomb. Remember, all of our units are going to be consistent, so we have to use kilograms, meters, seconds, newtons, coulomb, okay? So there's F, the force, and then we have mass times acceleration equals force. So that equals Q times E. Therefore, the acceleration is Q E over M, and it's constant. So you're going to plug some numbers in here. You're going to have electron charge on the first problem, proton charge on the other one, and electron mass on the first problem, proton mass on the other problem. Now they both have the same charge and their mass is different by like a factor of 1,000. But the point is that this is a constant acceleration. So we have to remember our kinematics. We have, yeah, in fact, I'll write them down. x0, v0t plus a half a t squared. And we're just going to start at the origin. And v is equal to v0 plus a times t. So in constant acceleration kinematics, this is your distance time law. This is your velocity time law. So we're going to start out at rest, at say an origin, at rest. So from this first equation here, remember the acceleration you have to plug, when you're done, you have to plug those numbers in. We're not done yet. Okay. So the acceleration, the time it's going to take now, given that acceleration, we're going to get t is equal to v over a, and I could call it v final over a. And in fact, they told us it was going to be 1%, I think, of the speed of light. Okay. But, you know, I want to put that here, though. V final equals 0.01 C. C is 3 times 10 to the 8 meters per second. Thing is, you don't want to plug any numbers in until you're done. So that's the time, and then you can plug that in and get it. Okay, I'll even give this a subscript. This is V final that we're asking for. And then the distance it travels in that time is going to be obtained here. Okay. So X final, whatever you want to call it, is equal to 1/2 A, and then this T squared. So V final squared over A squared. And that'll simplify. V final squared over 2A. Yeah, so only when you have these results would you plug in any of these numbers. Speed of light, again, this acceleration, charge, mass, electric field that's been given. Yeah. Okay, so good kinematics. And we'll be doing a little more kinematics because there are some interesting problems with the motion of charged particles throughout the semester. It plays a big role. In other words, launching electrons around. Later on we'll see they go in circles, they go in straight lines, they go in parabolas, they do a lot of interesting stuff. Good. So now let's talk about problem 81. Now 81 may have looked a little bit contrived, but it's an important physical scenario because it's an example of oscillations near an equilibrium, which is something you studied last semester, and we'll try to do a couple similar type of problems coming up soon. So this one was the following. They give you a tube. The idea with the tube is just to keep two charges, make it a little taller. So we've got an axis here. Okay. We've got an axis. There we go. Okay. We have a y-axis. And here's an origin. Okay, so there's a y-axis. And this thing has these two spherical charges that repel each other, and the equilibrium here is at y sub 0. Let's see if I've got this right. Yeah. Equilibrium at y sub 0, and one has a capital Q, one has a lowercase q, for whatever it's worth. Yeah, they have different charges. Q, but they're repelling each other. The whole idea is that they're in equilibrium. The tube just keeps them, from going off any which way. No friction. They're repelling each other, and this is an equilibrium. So the first thing for the equilibrium we're going to have two forces that add up to 0. Okay. We're going to have mass times gravity, and we're going to have the electric force, and they cancel each other out. So for equilibrium, we have F net equals KQQ divided by Y0 squared minus mg. Okay, that equals 0. And that will give us the y sub 0. That means y sub 0 is equal to K, Q, Q over mg square root, right, to the 1/2 power. So that's the equilibrium. But now the dynamics is what we're interested in. So it's an equilibrium. Imagine you give it a little push with your finger. They're claiming it's going to oscillate up and down, okay, with a certain frequency that they gave you. Okay. And Small oscillations near an equilibrium position are utterly important in physics. So let's look at this in the following way. So the dynamics, we're going to let delta y be equal to y minus y sub 0. Okay, delta y minus y sub 0, which we already found. And we're going to write this differential equation. Well, first we're going to write F net is going to be equal to k q over y squared minus mg. Okay. So this is different because I'm not saying the equilibrium position where it's 0, it's just a difference. Okay. So when y is equal to y sub 0, F net is 0, as we found up here, but otherwise, if you lift it up or if you push it down, you have a different force. Okay. So this is kind of a sophisticated problem. And here I'm just going to put a note, because you probably learned this somewhere in your mathematical career. Remember this. You learned that if y is equal to f of x as an approximation, you can write dy f prime of x dx, or delta y is approximately f prime of x delta x, where you're around, let's say, some x0 there. This follows right from the definition of the derivative. If you had a graph, if you had a graph of some kind of function here, x0, x, y-axis, then you'd just be constructing a difference quotient here, okay? So this is a really useful technique. We're going to do it for f net here of y, okay, because it's a function of y. So now delta f net is equal to f net prime of y sub 0 delta y. That's what we're going to do. Or, since it's a delta f net, it's f net minus f net 0. That's a delta f. Like I could have called this f net comma 0 right here because I was getting the equilibrium. Let me make a little more room. Okay, so directly underneath here, there's our function. I will place this down here. So we're looking at f net minus f net comma 0 equals, now we're going to take the derivative of this function at y sub 0. So that's y to the minus 2, y to the minus second power. So we have minus 2k q over y cubed, but since it's evaluated at that particular point, that's y sub 0 cubed times delta y. So that's our approximation. Now this, of course, is 0, right? It's 0 because it's at the equilibrium. It's where that balances out. So here's what we have. If we have m times d squared dt squared of our delta y is equal to minus 2k QQ over y0 cubed times delta y. So now I've just done Newton's law. I could have given this delta y another name. It's a new, it's y minus y0. Do I have it up there? Yeah, there. Could have given it any name at this point. This is the form of the harmonic oscillator equation. Mass times acceleration equals force. So, or d squared dt squared of this delta y is equal to minus 2kq lowercase q m y0 cubed times delta y. Or I'm just going to write, because you learned it this way last semester, recall d squared x dt squared equals minus omega squared x. That's the equation of the harmonic oscillator differential equation for the harmonic oscillator. So what is our omega squared? It's what I have here in parentheses. And if you take this expression, omega squared equals what's in parentheses, I'll write it down for you, equals 2k q m y naught cubed. Y naught given up there, then a couple steps of algebra and you get the answer that was in the book. But what's so important here is this system that's in equilibrium, and when you give it a little tap, it starts to oscillate. Okay? Because once you show that it has this form of differential equation, that is an oscillation. Okay? And so that's important. Omega squared, I changed the name from delta y to x, okay, because that's the way you guys learned it. And in terms of oscillations period, you have omega t is equal to 2 pi. So you get the period of oscillations, the angular frequency of oscillations. Okay, there should be a couple more problems like that coming up in the not too distant future. So those are good ones. It's kind of challenging, I admit, but if you got time, take a good look at it and try to understand it. Okay, I'm going to consult the clock. Okay, great. So that's time well spent. If you work these problems out and understand them, that's good stuff. Good review of last semester's work. We've introduced the electrical field, the electrical force, and the field. So let's see what we're going to do next. We're moving on into the new chapter, and it's about continuous charge distributions. So you'll notice we've been doing point charges. Okay? We've been doing point charges and vector addition and that kind of thing. Now we're going to do continuous charge distributions. Here, I'll clear all these guys. Continuous charge distributions. By the way, for these problems, you should write down some of what I said, especially this last one. Good problem. Okay. So this new chapter has a lot of great topics in it. Continuous charge distributions. I'll get started on a few. what are we talking about? What we had up until now, and what we were just discussing, were basically point charge distributions. And so we'll start with those. If we have point charges, we have what's called the principle of superposition. We have several charges, and to get the net effect, we just added all the vectors for electric fields and for electric forces. Okay. Point charges, F net is equal to the sum of F sub I, and the same thing if we're doing electric fields, E net would be the sum of individual charges. So that is really not going to change in principle, but we're going to have continuous charges, and therefore instead of a sum, we're going to have an integral. So we get to do some interesting integrations. So, and let's even write under here, say, E is equal to K, Q. In fact, it doesn't have to have a subscript, it's KQ over R squared. And it's in the direction, I'm just going to say R hat, it's in the direction of a vector R that goes from wherever your point is, your origin, to that point. So if we had some coordinate system here, X, Y, Z, there's the origin. And say we have a charge at the origin. Okay, so here we have Q. And out here, there's a vector R, and this is the unit vector. R hat equals vector R divided by its magnitude. Unit vector. So we're going to have to do something, yeah, and of course adding a bunch of these up can become pretty tedious. We're going to have to do something similar when instead of a point charge, we have a linear or continuous charge distribution. So this was for point charges, I'll say 2 here. For continuous charges, we have a charge density. So we have delta Q is equal to a charge density delta volume, so that's volume, or delta Q is equal to sigma delta area, or delta Q, and of course we'll turn this into infinitesimals for our integrals, but delta Q would be lambda delta L, so that would be for a length. So what you'd be talking about is density here would be coulombs per cubic meter, right? Charge per volume. This would be coulombs per surface area. This would be coulombs per meter, or charge per length. And the one we're going to start with is charge per length. Okay. So lambda, I'll just write charge per length. Let's see if we can do a couple of examples. I think the simplest one is not the one they do in the book first. The simplest one is if we're on the x-axis, I forget what they do, but let's just call it the x-axis, and we have a, maybe I'll consult what they do just a moment. Yeah. Yes or no? Hold on. Line charge. Yeah, they go from the origin. Good. So what we're going to do is have a line charge here's the x-axis, from minus L over 2 to plus L over 2. Okay. So this is a line charge, and this is minus L over 2, this is plus L over 2. And say we're out here at some point X, what's the electric field going to be? Well, by symmetry, if this is a positive charge, so we have a total of Q. If this is a positive charge, we're going to have a field pointing away. Okay, that much we know. But how do we get it? What we'll do is break it up into a bunch of little chargelets, and we'll have the following. I'll just write it down and then I'll explain it. So E is going to be EX times I hat, so the unit vector in X direction. And it's going to be integral. Now our delta Q, see, I want to compare it to this. Okay. We've got a K, we can pull the K out in fact. K constant, Coulomb constant comes out, so we need a charge there, and what that is lambda of X dx, because we're along the X-axis. So K lambda dx is going to be our KQ, and in the denominator we have the distance from this X point to some X prime in here. So I'm going to call this X minus X prime, the quantity squared. And I have to call it, since it's an integration variable, so I'm integrating over these X primes. The X is actually out here. Okay. These X primes are just from minus L over 2, minus L over 2, plus L over 2. I should leave this for you guys to do. Well, let's do it anyway. Okay. So what we're looking at here, we've got a K. The lambda is constant, but what is the lambda? Since this is a total length L, we have lambda equals charge per length. Okay. So it's just a charge per length. So I'm going to pull this lambda out, Q divided by L, and now I have to do this integral. Negative to positive L over 2 dx prime x minus x prime squared. So what's the antiderivative of that? K Q over L. We have 1 over x minus x prime. And if we take the derivative of that, we'll get negative 1 over x minus x prime squared. So that's a good antiderivative if we put a minus 1 in front, and minus L over 2 to plus L over 2. So continuing. So we want to evaluate this thing, and we have, continuing our equal sign, K Q over L. We've got a minus sign, that's fine. We have 1 over x minus L over 2 minus 1 over x minus negative, which is plus L over 2 times I hat. Now the interesting thing is we can't really see, well, we can see what we have, but we're no longer seeing the simple form of the point charge. So the question is, how do we get back to the simple form of the point charge? if we were far enough away from that little segment, it would, for all practical purposes, be a point charge. So for x much, much greater than L, we should regain the point charge. Point charge behavior, as we call it, behavior. So the function should look like it, but it doesn't look like a point charge right now, does it? Okay. So you have to work with this thing a bit in order to get the point charge behavior. And this is what we're looking for. We should end up with E going to K Q over X squared. That's what we're supposed to get in the limit as X is much greater than L. There are a couple of ways to do this. You have to work with this thing. You can do a common denominator, but probably better to multiply top and bottom by 2 over L. Okay. So E equals minus KQ. Everything has to come out in the wash. So if we multiply the numerator by 2 over L, the denominator by 2 over L times everything that's there. 2 over L here is going to cancel that one. In the denominator, 2x over L minus 1 over 2x over L plus 1. Okay. But yeah. Here's your exact answer, and you simplify it to get an exact answer, and then take the limit where x is much, much greater than L, and you have to come out with this. Let's check the clock again. Okay, the other one I want to do, so let me put this in words. Well, I did put it in words. I just want to stress it. You want to get this behavior by taking an appropriate limit. Yeah. Good. So the second system I want to do is, so next, is if we have a ring. So ring of charge, and we want to be along an axis here. So I could have this ring of charge, radius R, or maybe they use A in the book, doesn't matter, radius A. So the charge is right here, and again, if we're on the axis, we're going to have that symmetry, and we're going to be able to say that out here at X, all of the contributions from different points of the ring sum up to an X direction contribution, because if you're up here, you get one that cancels if you're down there. You get the cancellation the same way we had earlier in the hour. Okay. So this is the one we're going to do a couple of homework problems on. I didn't find any homework problems for this one. So I'm going to go ahead and write down the homework. Oh, let me first say something here. We're going to have to do an integration just from 0 to 2 pi. It's actually going to be a trivial integration, because we can see by the symmetry that these things from opposite sides of the ring cancel and only leave an x component. Okay. So we will have a effect. So I don't actually have to write out the integral. We will have something like this. From this point here, we'll have a vector, and from that point there, we'll have a vector. And the projection of these two will be in the forward direction. So if this is distance A, and this is here distance x, we have, and this is r, we have a k, lambda a d theta, okay, charge per length times angle, which is dimensionless. So that'll give us the q. We have an r squared, and then we have to multiply by the cosine of theta here, which will give us the forward projection, same angle here and here. So cosine of theta is equal to x divided by root a squared plus, well, actually just x divided by r for the moment. Okay, x divided by r. X divided by r. Okay. So that goes there, and then the integration is trivial. You go from 0 to 2 pi, you're going around this circle, and you're just getting lambda a d theta is going to turn into q. Okay. So you're going to end up with k e sub x, you're going to have k q, that cosine theta that I've talked about, r cubed, I mean x over r cubed, x over r cubed, okay. And you're going to have r is equal to root a squared plus x squared. Okay, so that's in the book. That's the quick construction of it, and I want to put a couple homework problems up for you guys to solve using that example there. Let me make sure we know which one it is. Yeah, this is example 22.5. They use the z-axis, oh well. Same thing. Okay. I'll go ahead and put those things together. We're using x, they're using z, that's okay. So e sub x, e vector equals e sub x I hat, because we're using the x-axis right there. We have, like I said, trivial integration gave us k total charge. The r cubed right here is a squared plus x squared to the 3/2 power, and we have x right there. Okay. Good. Anything else? Let me go ahead and, yeah. And since we're calling it the x-axis, we're doing I hat. So this is the field we're going to do some homework problems on. Let's see what I had for you guys. $74 and $80. Okay, let's consult. Yeah, these are all good. We're going to do all three of them. So homework, this is the 10th lecture. Chapter 22, problems 20, 74, and 80. Yeah, I kind of rushed through this at the very end, but I wanted to get here. These are thematically similar to that oscillation problem we did, among other things, so they're good. Okay, see you guys next time.